design and inference of scene representations for video compression. The approach that we are taking is to assume that for a given video there exists an underlying scene. We wish to partition this scene into two types of regions. Regions which we call visual structures that exhibit temporal redundancy, and regions which we call visual textures that exhibit spatial redundancy. In this work, we take advantage of the temporal redundancy of visual structures to improve over the compression performance of both HEVC and H.264. A companion paper exists in the literature that shows how exploiting visual textures can give additional performance gains. Before we dive into the solution we are proposing, let's briefly talk about how important video compression and video content are. In particular, Cisco projects that video traffic will be 77% of all internet traffic in 2019, and there will also be 5 million years of video content crossing the internet each month. It is therefore undeniable that video content will dominate internet traffic in the next few years. Current technology used in video encoders such as H.264 and HEVC will eventually start producing diminishing returns. In order to cope with the increasing amount of data, a different approach would need to be followed. We believe that instead of modeling pixels as is traditionally done in current encoding schemes, we could instead model higher level region types such as structures and textures, which would allow us to improve over existing technology. Today we focus on our treatment on structures. We define structures as regions in images that have two properties. First one, they trigger isolated responses of a feature detector that generate regions of interest such as blobs, corners, and so on. And these regions persist in more than one image. Therefore, structures can be generally thought of as the salient regions of the video. Using an appropriate tracker, we can detect and track points over the duration of the video. In practice, a structure region is represented by an image patch surrounding the tracked point in each frame as shown in the lower figure. To reduce the redundancy of this representation, we choose to represent structures using a time-invariant representation. In particular, we use the time average of the patches around each tracked point, which we call a template. This process produces a collection of templates, one for each tracked point. At decoding time, we can back-project these templates on the video frames. However, if we do this in an arbitrary order, the reconstruction error is not necessarily minimized. In this paper, we try to determine the back projection ordering that minimizes the reconstruction error. This can be done efficiently by assigning each template to a depth layer. This considerably simplifies the problem and allows us to solve it efficiently. The problem is solved by setting up an MRF. The optimization involves minimizing a cost function that optimizes the reconstruction error, penalizes large depth orderings, and satisfies certain pairwise terms that meet the ordering constraints. We minimize the cost function using a discrete optimization scheme, TRWS. This is a typical example of the output of the optimization where the MRF splits the input frames into layers. At reconstruction time, the layers can be overlaid to reproduce the input frame. Using our method, in conjunction with HEVC and H.264, we're able to outperform both of them in a PSNR versus bitrate comparison in the Mosaic dataset. The bottom row shows the regions of frames where we get most of the compression benefits using our method when compared to HEVC. Here is a comparison of our method against HEVC, both having the same file size. And in case you couldn't see much detail due to the projector, here are some regions highlighted. In particular, the window and the woman's shirt are considerably better encoded using our method. Finally, I want to mention that after decoding the structures, we can use a texture synthesis algorithm to synthesize the rest of the image frames and achieve even further performance gains.